Ancient people saw them as messages from the gods, as supernatural winds that blew from the realm of spirits. Modern science has linked these polar light shows, called auroras, to vast waves of electrified gas hurled in our direction by the sun. Today, researchers from a whole new generation see this dynamic substance, plasma, as an energy source that may one day fuel humanity's expansion into space. What can we learn? And how far can we go? By tapping into the strange and elusive fourth state of matter. A small cadre of scientists has come to Fairbanks, Alaska, to realize what may seem an impossible dream: to revolutionize space travel.
Actually cool.
Dr. Ben Longmire and his team from the University of Michigan have designed a whole new type of rocket engine that promises a faster and more efficient way to get around in space. They're here to test components of this rocket by sending them aboard helium balloons to an altitude of 30 kilometers into the harsh environment of space. Above the North and South poles, conditions are about as harsh as you can get. Our planet is bombarded with a steady stream of charged particles from the sun. Earth's magnetic field accelerates and channels them, turning the night into a spectacle of color. While most astronauts train to live and work in zero gravity, or to move around in bulky spacesuits, these would-be space explorers are preparing to negotiate some of Earth's harshest environments. Once they launch their payload, it will rise slowly into the upper atmosphere. After drifting through the night, above 99% of Earth's atmosphere, the payload will detach from the balloon and parachute down to the ground. The team must be prepared to retrieve it across a large stretch of Alaska's snowy wilderness. To understand the revolutionary nature of the idea they are pursuing, we go back to the dawn of rocketry. In over 100 years, the technology of a rocket has hardly changed. Fill a cylinder with volatile chemicals,
Contact! Yes,
then ignite them in a controlled explosion. The force of the blast is what pushes the rocket up. Nowadays, chemical rockets are the only ones with enough thrust to overcome Earth's gravity and carry a payload into orbit. But they're not very efficient. The heavier the payload, the more fuel a rocket needs to lift it into space. But the more fuel a rocket carries, the more fuel it needs. One of the fabled Saturn V rockets of the Apollo era, for example, weighed in at 177,000 kilograms. Filled up with fuel, it weighed almost 16 times that. The space shuttle, with maximum payload, weighed about 100,000 kilos. Add tanks and fuel, and it lifted off at 2 million kilograms. Regardless of weight, for a spacecraft to escape Earth's gravity, it must reach a minimum speed of 40,000 kilometers per hour. The energy needed to do that meant there wasn't enough fuel for a sustained acceleration to more distant planetary shores. Most missions beyond Earth have relied instead on their initial launch speed to coast to their destination. The twin spacecraft of Voyager, for example, did not have enough speed to reach their current positions at the edge of the solar system. To give them a boost, flight planners sent them into Jupiter's gravitational field, using its pull to slingshot them out to Saturn. Voyager 1 used Saturn to accelerate to almost 63,000 kilometers per hour. Voyager 2 got further assists from Saturn and Uranus. Ben's rockets promise far greater gas mileage than traditional chemical rockets, but with enough power to reach distant targets more quickly. The idea is that once in space, his rockets use electricity to create a weak force, which over time can accelerate them to very high speeds. They run on the same fuel that nature uses literally to power the cosmos. Not long after its explosive beginnings, the universe was awash in vast stores of hydrogen gas. But even as the universe continued to expand, gravity drew clumps of matter into ever denser concentrations. The earliest stars took shape, immense balls of hydrogen gas hundreds of times the mass of our Sun. As they contracted inward, they heated up and ignited. Intense radiation now began to flow through the voids. That had the effect, all through the universe, of stripping electrons away from the primordial gas. The universe became filled not with solids, liquid or gas, but with a fourth state of matter, plasma. On our planet, plasma occurs only in rare circumstances. In a hot flame, a bolt of lightning, or in a blown electrical transformer. Made up of negatively charged electrons and positively charged ions, plasma is in most cases electrically neutral, since the charges balance each other out. That led the physicist Irving Langmuir in the 1920s to compare it to the clear liquid plasma that carries blood cells through our bodies. The development of radio led to the discovery, high above the Earth, of a natural plasma ceiling, the ionosphere. It hovers above us, reflecting some radio frequencies and absorbing others. Its importance became clear when engineers noticed that radio waves could, under some conditions, travel beyond our line of sight. They discovered that signals could be bounced deliberately off this conducting layer in what's called skywave propagation. In World War II, a whole new age of global communications came of age when radio was used to execute complex worldwide logistics of troop and ship movements. The presence of the ionosphere is due to a steady stream of charged particles, or plasma, that comes from the sun. A spacecraft with complex computer components must be able to survive constant exposure to these particles. As part of their design process, Ben and his team want to test some of the specialized components of their rockets in the plasma-filled environment of our upper atmosphere.
Got it down. I think it's just the sun.
Yeah, I think that one's okay.
Alright, yeah. I'll wrap the middle one though. Or I can just wrap it. I just
These components will be mounted on a simple frame attached by rope to a high-altitude balloon.
Hold on, they're not oriented the same.
The frame is also outfitted with an array of novel sensors to take independent readings. One holds a colony of bacteria.
The idea is that the bacteria itself can detect radiation. So it mutates in a certain way or in a very known way that when you send it into an environment with a lot of cosmic rays and a lot of perhaps X-rays from the aurora itself, it mutates. And so we'll detect sort of the level of radiation that it's exposed to by looking at these mutations after we recover the bacteria from flying it to the edge of space in these balloon capsules.
Jordan, you got the camera, or wait a second.
Another is a series of tiny GoPro cameras converted to record the intensity of infrared and ultraviolet light, normally hidden from the human eye.
We want to kind of puff up so we know it's replaced all the air.
The team uses argon gas to insulate instruments against the cold, with chemical packets added for warmth.
So this test is doing normal video, version 70 firmware.
They stabilize the frame with tiny gyroscopes and outfit it with GPS devices for tracking.
Cool.
This team is doing much more than just designing instruments to survive a rain of charged particles. Their goal is to design spacecraft that actually harness the explosive properties of plasma. Unlike most matter on Earth, plasma conducts electricity and responds to magnetic fields. In space, these properties influence the formation of structures like galaxies and nebulae. and they play a role in some of the most violent processes in the universe, such as the formation of a black hole. It forms in the wake of a giant star's death, when matter collapses into its core. It swirls in along what's known as an accretion disk. Magnetic fields take shape on the disk, rising and twisting around the polar regions. They draw huge volumes of plasma up, then shoot it out at high speeds. These plasma jets can extend far beyond the largest black holes. You can see them blasting continuously from the centers of galaxies, reaching thousands of light years into space. Studies of one giant nearby ball of plasma show what a complex and volatile substance it can be. In the core of our sun, high heat and crushing pressures cause hydrogen atoms to crash together. That sets off a nuclear reaction in which hydrogen atoms fuse into heavier ones like helium and carbon, generating heat. This heat slowly rises to the surface of the sun in vast plumes of plasma. You can see evidence of this process, called convection, in a pattern of ever-evolving blobs known as granules. They are like the tops of thunderstorms. Even as energy builds within, the sun's gravity and density can stifle its escape.